AP Biology. Today we're going to discuss general chemistry as it is applicable to the study of biology. First thing we have to talk about is life, the universe, and everything. The answer is 42. If you don't get that, you're a sad, sad science student. But seriously, what you have to understand about everything in the universe is made of one of two things, either matter or energy. We'll talk about energy in some detail later on, but for now, we wanted to talk about matter. All right. Specifically, matter can be defined as anything that has mass and takes up space. What matter is actually made of is atoms. All right. You've heard of atomic structure. You've all heard of atoms before. Atoms basically have three subatomic, lower than atom components. They are electrons, which are negative, and functionally have no mass. They actually do have a mass, but it's very, very small. And so we can discuss them, except at the most exquisitely detailed level, as having no mass. Neutrons are neutral, which means that they carry no charge, and they have a mass of 1 atomic mass unit. Now, subatomic particles are so small that typical measurements that we have, such as grams, micrograms, milligrams, all that stuff, it's just too big. And so we have a mass unit called the atomic mass unit, where a neutron weighs 1, and so does a proton. And so we use those things to determine the mass of specific atoms and elements. Which leads us to the last component, which is the proton. It, again, has mass, 1 atomic mass unit, and it has a positive charge. All right. And what you can see on this diagram over here, just basic atom. I mean, this is carbon. It's just meant as an example. Inside here, which is where you have the protons and the neutrons, is the nucleus. All right. Now, the nucleus is the center of an atom. It's the smallest component, but it's also where all the mass of the atom is. Surrounding the nucleus are clouds, and these clouds are where the electrons orbit. Functional thing about chemistry and understanding molecular structure and atomic structure. You won't ever know exactly where the electrons are. So we speak about where they are in terms of clouds because they're constantly in motion around the atom. And what we do is we just tell you where they're most likely to be found. Whereas the nucleus, which contains the protons, the neutrons, all the mass, and the positive charge, actually is inside in a very small place. In fact, it's so small that if you were to imagine a football stadium and then think about having a pushpin at the 50-yard line of the football stadium, the stadium is the electron cloud and the pushpin is the nucleus. All right, that's the sort of space ratio we've got going on here. Now, granted, this is all still ridiculously small, but that's to give you a sense of how the nucleus compares to the overall electron cloud. All right. Now, let's talk about specific atoms, all right? There's a variety of atoms in nature. There's 114, I believe, at this point that are known or discovered or predicted. They're on the periodic table. I mean, you've seen this. You know the basics there. What you need to understand, and it is most important about elements, is that elements, which element it is determined by the number of protons. 1 proton is hydrogen, no matter what else goes on. 2 protons, helium, no matter what else goes on. 6 protons, carbon, no matter what else goes on. 8 protons is oxygen, no matter what else goes on. The element is determined by the number of protons. Okay? You need to know, and you should know at this point, that carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are the 6 most common elements found in living tissue. There's lots of other elements that are found in living tissue, but the majority of organic molecules are made of carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. So you really need to make sure that you know everything about those 6 elements, okay? A couple of ways that we can vary elements. You can have an element that is an isotope. I said that protons determine the atom and the element it is. But within each element, they have to have a certain number of protons. They could have a different number of neutrons. So you could have, for instance, carbon, which is the most common one, has typically 6 protons, 6 neutrons. That gives it a mass of 12. But a carbon that we're generally familiar with, which is carbon-14, which is used for radioactive dating, it lets scientists determine how old something is. That means that carbon has 6 protons. It has to, it's carbon. But it also has 8 neutrons, okay? Another example you could see over here, you've got helium. The red right here is the positively charged proton, and the yellow right here is the neutron. Well, here you've got a helium that's got 2 protons, 3 neutrons. It's 5 helium because its mass is 5. Well, over here the mass is 6. Well, since it's helium, the number of protons can't change. So the number of neutrons must change. So you got 1, 2, 3, 4, and 6. 3 neutrons, 4 neutrons. Over here, 1, 2, 3, 4, 5 neutrons. Down here, 1, 2, 3, 4, 5, 6 neutrons. These are all isotopes, okay? Now, isotopes have a lot of uses. They're heavier, so they actually, when you use certain isotopes, you can use them if they're heavy enough for centrifugation, separation. Also, isotopes tend to be radioactive because the bigger the nucleus gets, the less these subatomic forces are able to hold it together. And so pieces tend to come off, and that creates radiation, which we can use to track things, okay? They actually did it in the Hershey-Chase experiment. They used radioactive isotopes when allowing the viruses to assemble. All right, so that's basically an isotope. Next up on our list is ions. So if you can vary the neutrons to get an isotope, you can vary the electrons to get an ion. First thing you need to understand, all elements begin with a number of electrons equal to the number of protons. And then when you vary that number of electrons, you can create a charge. Now it's very important. If something has a positive charge, it loses electrons. And if it has a negative charge, it gains electrons, because electrons have a negative charge. So if everything has the same number of protons and the same number of electrons to start, 6 protons in carbon, 6 electrons in carbon, the charges cancel each other out and the atom is neutral. But if it were to gain an electron, there's more negative charges than positive, so the element is negative. If it were to lose an electron, there's more positive charges, more protons than negative, it's positively charged. Okay? Remember, if it gained a proton, it wouldn't be positively charged. It would be a different element. All right, so now we need to talk a little bit about bonding. Everything in nature needs to move to what's called the lowest energy state. That's a fundamental law of thermodynamics. Nature wants to be in the lowest energy state. Well, the majority of elements are not in the lowest energy state. And so what they do to get to the lowest energy state is to join together. They create a molecule, which is 2 or more elements that have been joined together, to enter the lowest energy state. So forming molecules can be a natural occurrence as long as that formation leads to a lower energy state. When 2 elements join together, we call this a chemical bond. And a chemical bond is something that gets each element to a lower energy state. And this is very important. Molecules have different chemical properties than the individual elements that make them up. Sodium chloride, table salt. We all know what table salt is. It's crisp. It's a crystal. It tastes excellent on steak. All right. But it's an ionic compound. It's an ionic molecule that has unique properties. The individual elements that make up sodium chloride, table salt, sodium is a white powder that's explosive when mixed with water, and chlorine is a poisonous gas. Sodium chloride, neither of those things. So when you create this chemical bond, you not only get to the lowest energy state, you create a series of new chemical properties, and that's important to understand. Chemical bonding is determined by what's called the valence shell. All right. Electrons that surround the nucleus of an atom are organized into shells. Yes, I told you they move at random. We don't always know where they are, but we do know sort of the general location, and we call that general location a shell. The outermost shell of any element is known as the valence shell. One of the ways that we can dictate lowest energy state is if the valence shell is full. So you take a look over here, right? These 4 electrons are in the outermost shell. Okay? Since they're in the outermost shell, they are the valence electrons. Well, for a full valence shell, elements either want 2 electrons or 8 electrons. Now, 2 electrons only applies to certain shells, and that's basically all of these. All right? But it really only applies to this because 1s is dealt with alone. This is the second shell, 2s and 2p. This is the third shell. All right? So basically, what needs to happen is that the first 2 elements on the periodic table, hydrogen and helium, both need 2 electrons. So hydrogen and helium. Everything else, for our purposes, wants 8 in its valence shell to be full. Now, if it has 1 or 2 electrons, it's actually more likely to lose them so that the shell underneath becomes the valence shell. And then since it was full already, the valence shell will be full. Because the shells fill, the first shell fills before the second shell gets used, if that makes sense. All right. So if we're in the outermost shell, all the shells underneath are already filled. Okay. Now, there's 2 main types of bonds I want to talk about here that all involve the valence shell. The first one is the ionic bond. Some atoms that have very few valence electrons, a great example is sodium, are very likely to lose them. You can see this right here. Sodium has 1 valence electron. Notice this. 1, 2 in the first shell. 1, 2, 3, 4, 5, 6, 7, 8 in the second shell. 1 more. So it only has 1 in its outer shell. It's very likely to lose that electron. And when it does, it'll have more protons than it does electrons. Okay? Remember, you can tell the number of electrons it will have by the number of protons it does have. When it loses that, now this shell with 8 right here would now be the outermost valence shell, and it is full. So even though it has a positive charge, it is at the lowest energy state. Now, atoms that have almost full valence shells, like chlorine over here, which has 1, 2, 3, 4, 5, 6, 7 in the outermost shell, they are likely to take this electron and add it, like you can see right here. Now, it has 8 in its valence shell. It is full and has a negative charge. Just like a magnet, 2 atoms that have a charge, positive and negative, those charges attract the elements to each other. That forms a chemical bond that we call an ionic bond. All right? The second type of bonding I want to talk about is covalent bonding, where in ionic bonding, the elements lose or gain electrons. They literally get rid of them or take them unto themselves. Covalent bonds are for elements that don't really gain or lose electrons easily. So instead, they're going to share the electrons. These electrons will literally orbit the nuclei of both elements as one big cloud. It's actually a hybrid valence shell. And what it does is it sort of gives the element the illusion that it's got a full valence shell. And that is a lower energy state. And so that's why it happens. Some great examples over here. This one actually is chlorine. All right, this is chlorine and this is chlorine. Since they have 7 each, they take these 2. They spend some time over here. This one thinks it's full. They spend some time over here, and this one thinks it's full. Both of them think they're filled. They're sharing. Full valence shell, lowest energy state. Same thing with water. Hydrogen, which actually only has the first shell, only needs 2 in the first shell. So it has these 2, and it thinks, hey, I'm all filled up. This hydrogen has these 2 and thinks, hey, I'm all filled up. Oxygen's got 1, 2, 3, 4, 5, 6, 7, 8, and it thinks, hey, I'm all filled up. Everybody thinks they have a full valence shell. Everybody's the lowest energy state. Okay? And you can see, sometimes this is a one element to one element bond. Sometimes it's one element to multiple elements. And that forms a hybrid shell. And what happens, we're going to talk about this more in the properties of water, is electronegativity. The pull of one nucleus over the other can actually create a polar bond, which gives them a slight charge. And that's it for now.